Hi all, let's do one more example of a word problem involving a quotient rule. And I think this is an especially good one because this asks for a first and second derivative. So we have a function that inputs the number of hours after an injection is given to a patient, and it outputs the concentration of the drug in their bloodstream. So we're supposed to find and interpret C prime of 3 and C double prime of 3. I'm just going to jump in and start trying to find those C primes. So our C formula is 0.14t over t squared plus 1. If we want to find the derivative of this function, it is a quotient, so we should use a quotient rule. So we will have the bottom squared, and then in the top we'll have the bottom again, times the derivative of the top, which is just a 0.14, minus the top, 0.14t, times the derivative of the bottom, which is a 2t. So not too bad, but we do have that sort of like partly factored, partly sum and difference thing going on. So I think I'll go ahead and distribute that 0.14 through. I will get a 0.14t squared plus 0.14 minus a 0.28t squared. And that is all over a t squared plus 1 squared. So I can do a little bit better with that numerator. I can combine the 0.14t squared minus 0.28t squared, and I get a 0.14 minus 0.14t squared. The denominator is a t squared plus 1 squared. If you want to cancel, especially when you're going to be taking a second derivative. So I am looking at this and thinking, well, if I factored out a 0.14, would that help me? But it doesn't quite. I get a 1 minus t squared, and I really need a 1 plus t squared to be able to cancel. I can't factor out that denominator anymore. That t squared plus 1 doesn't break down. So I think I am actually pretty stuck here. Okay, so now we're ready for a second derivative, and we'll still need to come back and plug 3 into both of these functions, but I want to do all my derivative work first. So looking at c prime of t as my starting function, to find a second derivative, you just start over and pretend like c prime is your original function and apply shortcuts to it. So since c prime is a quotient, I am going to set up a big old quotient rule. So I'll have a t squared plus 1 squared, and then squared again would be to the 4th power. And then I'll have a t squared plus 1 squared times the derivative of the top, which is a negative 0.28t. And then I have minus the top, 0.14 minus 0.14t squared, times the derivative of the bottom. This is a little tricky. We'll have a chain rule soon, and it'll give us another way to tackle this. But for now, we would have to multiply this out. We can't take the derivative of a function raised to a power. We don't have enough shortcuts to deal with that. But we can FOIL this out and say, okay, that's t to the 4th plus 2t squared plus 1. So its derivative is 4t cubed plus 4t. So that is doable. Our big goal is just to plug a 3 into this, but I want to continue to sort of preview some of the trickier simplification that we can do. So I am noticing something here. This last derivative that I wrote down, I could factor a 4t out of it, and I'd be left with a t squared plus 1. And the reason I think that's so interesting is because the top of this fraction is made up of 2 really messy terms, and the term before the subtraction has a t squared plus 1, and the term after the subtraction has a t squared plus 1. I'm also actually noticing that both have a t in them. So one thing we could do to try and simplify a little is to factor out of that entire numerator a t and a t squared plus 1. So if we do that, we're looking first at before the subtraction sign. So one of those t squareds plus 1s is gone, and the t is gone. So that leaves me with a negative 0.28 and a single t squared plus 1. After the subtraction, if I've taken out the t and the t squared plus 1, all that I'm left with is that 4 out at the end and the 0.14 minus 0.14 t squared. The reason this is nice is because I can actually cancel out a t squared plus 1. So if I cross that out, I'll be left with 3 in the bottom. And then I can also do a little bit better inside the brackets. I have a negative 0.28 t squared minus 0.28. And then I have a negative, what is 4 times 0.14? 0.56. And then it becomes a plus 0.56 t squared. Okay, so when I'm all done simplifying, I think this might be a final step. I have a t out in front. In the brackets, I have a negative 0.28 t squared plus 0.56 t squared, so that becomes a positive 0.28 t squared. I have a negative 0.28 minus 0.56, which is a negative 0.84. You could factor a 0.28 out of that, I think, or maybe a 0.14, but I'm not too worried about it. I'm going to leave it. And then I did clean up the bottom just a little bit. I got it down to a t squared plus 1 cubed. So a little bit nicer for plugging in, but again, more about just giving you practice looking at some of the more complicated simplification that we have to do in this class. Really what we want to answer here is what is c prime of 3 and then what is c double prime of 3. So I'm going to plug 3 back into that derivative function. I got about negative 0.0112. And remember, that is, what were we doing? Concentration. Let's go up and look at units. Milligrams per cubic centimeter as a function of time. And what were our time units? Hours. So this is change in concentration over change in time. So I would say that at the 3-hour mark, after getting the injection, the concentration in the patient's system is dropping by 0.112 milligrams per cubic centimeter per hour. That's what that's telling me. Let's do the same for c double prime, and that can be a little trickier because we're interpreting second derivatives. And this one's a fairly tiny number. I got about 0.0504. Okay, so if I'm going to explain what that means, I'm going to round that off to 3 decimal places. That is the top was a c prime value. So I'm going to make it a fraction. This time we aren't starting with the c of t on our x and y axis. We are on our x axis because that doesn't change. So this is still hours. But the function we started with was actually the rate of change function. So this was milligrams per cc per hour already. Let me just make sure I got those units. Milligrams per cc. Yes. So when we take the derivative, this is how fast that rate, milligrams per cc per hour, changes each hour. So this is a question of, is the concentration, what was it doing before? Decreasing. Is it decreasing more and more slowly, or is it decreasing more and more quickly? What's happening to the rate? And since this one ended up being positive, it looks like the rate is increasing, but since it was negative, a less negative number is increasing. So it's actually slowing down. But we don't even have to get into that wording necessarily. I can say that at the 3-hour mark, and I should be careful, this is c double prime of 3 equals. At the 3-hour mark from getting the injection, the rate at which the concentration is decreasing is actually increasing or slowing by 0.005 milligrams per cc per hour each hour. So there should be a per hour at this point. This is kind of equivalent to acceleration, but you shouldn't be saying acceleration unless it's a distance, rate, time problem. Okay, so those are tricky. Hopefully having another one in your examples helps you a little bit thinking about it. Thanks for watching.